Yep. Okay, so I don't, this one's a little bit shorter, this review is, because we've got fewer sections, so I don't think we've got to worry about time or anything. Anybody think of any just general questions before we start going through the problems? Can't think of anything? Okay. All right, so just start working through these, I guess. Okay. So number one is find the absolute maximum and the absolute minimum. The only thing really different with that than on a problem where we're just finding local values, this is what we call them in here at level, is that we have to include the endpoints. Okay. So we know that if we have an absolute maximum or absolute minimum, it has to occur either where the derivative is 0 or undefined, so at the critical numbers, or at the endpoints. And so our first thing we need to find is the derivative. Okay, so let's see, 12x squared minus 12x minus 72. Website gave me some not great numbers on this one, around a little bit big. We got that factor of 12 though, will help. Okay. So we want to find the critical numbers. Okay, so that's where our derivative equals 0 or where it does not exist if we have any of those places. Okay, and then we will check each one of those critical numbers as well as the endpoints. Whichever one gives us the biggest value is the absolute maximum. Whichever gives us the smallest value is the absolute minimum. Okay. So this one's not super simple to solve for 0, but luckily we do have a common factor. Set that equal to 0. We can help ourselves by taking out a common factor of 12 here. You could do quadratic formula if you wanted to. The numbers get a little unwieldy, but you could do it. 12 times 6. Oh. Just factoring out a common factor of 12, and then that makes it easier to factor the trinomial part. I'm going to go over here, I guess. And so let's just say we'll divide both sides by 12 and get rid of that constant factor of 12. And then we need to factor the trinomial part. So we need factors of negative 6. That will add together and give us negative 1. Negative 3, positive 2. Yeah, negative 3, positive 2. Okay. Set each factor equal to 0 and solve. So we'll get x equals positive 3. X equals negative 2. And those are our critical numbers because there's not anywhere where this one would not exist. A situation where our derivative would not exist is if we have some x value that would make our derivative undefined. It's just a polynomial, so we don't have that on this one. Okay, so what we want to do, we want to take our critical numbers and the endpoints, negative 3 and 4, plug those into our original function and see what gives us the biggest and the smallest value. be our absolute maximum and absolute minimum. So we got 3, -2, -3, and 4. So go here. Our function's a little long on this one, so it makes it a little bit of a hassle, but not too bad. What we had 4x cubed minus 6x squared. And minus 72x plus 1. Wish I would have brought my calculator on this one. We'll see, we'll get through it. So it doesn't matter what order we do, I'm just gonna, I guess I'll do 3 first. 3 cubed is 27, so 4 times 27 minus 6 times 3 squared, so times 9, minus 72 times 3 plus 1. So if we do f of 3, I'm getting negative 161. I'm just plugging in for x. Let's see if we do f of -2. Let's see, so that's 4 times -2 cubed is -8, minus 6 times -2 squared is 4, minus 72 times -2 plus 1. That one I get 89. I want to double check these before you take them to the bank because I'm just using my phone calculator up here and I can do goofy things sometimes. And let's see, so -3 will have 4 times -27 minus 6 times 9 minus 72 times -3 plus 1. That one I got 55. One more to do. Do f of 4. So let's see, 4 times 4 cubed is 64 minus 6 times 16 minus 72 times 4 plus 1, negative 127. That one. So what's our absolute maximum? We'll do that first. 89, yeah, that's the biggest. So that's our max. And then our absolute minimum, negative 161. Yeah. So it took a minute, but it wasn't too bad. Kind of the arithmetic part of that was the worst part. So find the derivative, find the critical numbers, check the critical numbers in the endpoint in the original function. Yes, that's, yeah, so forget which one of the theorems, but it says if we have absolute or minimum or maximum, it either occurs where the derivative is 0 out of the hill or valley or at the endpoints. So those are the only places we have to check. Yes, we got somewhere where it's undefined. Give you 2 of these? Okay, well. I don't think I realized I gave you 2 absolute problems. Same drill, yeah. Find the derivative. And get 12x cubed minus 12x squared plus 24x. This time when we set our derivative equal to 0, we have, well, for some reason we also have a common factor of 12, but not only 12, we have a common factor of 12, what? 12x. Yeah. So we can factor out the 12x. That'll leave us with x squared minus x minus 2. Set that equal to 0. And factor the trinomial part, so we need factors of -2. That will add together and give us -1. So x minus 2, x plus 1. If we set each one of those equal to 0 individually and solve, we get our 3 critical numbers. We get x equals 0, x equals +2, x equals -1. And then we also want our endpoints in here, so we'll check -2 and 3. So sadly, we got 5 of these we got to do this time. Okay. 3x to the 4th minus 4x cubed. And then minus 12x squared plus 1. That's our function. So just one easy mistake that's easy to make when we're taking these values and plugging them back in, we're plugging them back into the original function, not the derivative. Okay, so f of 0 will give us 1. That one's easy, because all the x terms go away. Let's see, f of 2. Okay, so 3 times 16, that's 2 to the 4th, minus 4 times 8, minus 12 times 2 plus 1. Get -7 on that one. Then we need -1. That one shouldn't be too bad, so that'll give us 3 plus 4, because we have -1 cubed is -1 times -4 gives us plus 4. And then minus 12 plus 1. -4 on that one. And we got to do our 2 endpoints. Okay. So let's see. So 3 times 16 minus 4 times -8 minus 12 times 4 plus 1. 33 on that one. And then F3. So 3 times 81 is 3 to the 4th minus 4 times 27 minus 12 times 9 plus 1, 28. So, if you're doing those in a better calculator and not on the phone, it's easy because you can just go back and replace where you plugged in. So our absolute max, 33. Yep. And then absolute minimum, -7. Okay. I won't give you one that's too crazy to solve for 0 or anything. So. And it's not algebra class. So. I like algebra, but it's not what we're working on in here. Okay. Number 3, dealing with Rolle's theorem, says make sure it satisfies the 3 hypotheses of Rolle's theorem. And then if it does, find out number C that satisfy the theorem. The 3 conditions, we need our function to be continuous on the closed interval. It is because it's a polynomial. We need our function to be differentiable on the open interval. It is because it's a polynomial. So really the only one we need to check, okay, for Rolle's theorem, the third thing says that when we evaluate the function at the 2 endpoints, we get 0. So we need f of -1 and f of 3. If we check those, that'll be 2. But, did they come out that they equal 0 or did they equal each other? So that's 2 plus 4. Yeah, so maybe it's that they're equal to each other. Did I misremember the theorem there? They're both the same, not that they equal 0. That's right, yeah. Okay, sorry about that. So we've got to make sure they're both the same. Okay, that's good because it wasn't going to work the other way. So let's see, that's 2 plus 4 plus 7, so that's 13. And then F3, we get 18 minus 12 plus 7, so that's 13. Okay, so there's our third condition. Okay. The part we really want on this, we want to be able to find the C value. Okay. What Rolle's theorem tells us, this is where I was getting 0 in my head, is that there's some C in the interval, so that f prime of C equals 0. Okay. So C is some number in the interval -1 to 3. So we want to find that C value. So first we need f prime. This one, that's 4x minus 4. What we really want to work with is f of C, so f prime of C, so we just switch x to C. And Rolle's theorem tells us there's some C in here, so f prime of C equals 0. So this is f prime of C, so we just set it equal to 0 and solve. So because of Rolle's theorem, 4c minus 4 has to equal 0. So 4c equals 4. So c equals 1. And that is in the interval -1 to 3. I'm not going to try and trick you on Rolle's theorem. I will, let's see, how will I word a question like that? I will. You just need to remember on Rolle's theorem, that tells you this. For some C in the interval. That's mean value theorem. Yeah, we got one coming up. Yeah, it's mean value. Okay. So Rolle's theorem is really like a special case of mean value theorem. On Rolle's theorem, we require the endpoints are equal. So that means we've got a horizontal tangent line somewhere in there. mean value theorem, we don't care if the endpoints are equal or not, but we say that we've got a tangent line that's parallel to the secant line through the endpoint. So Rolle's theorem is the one where the derivative's got to be 0 somewhere in there. Let's see. 4. It's about the mean value theorem here. And yes, this one's continuous on 0 to 2 and differentiable on the open interval 0 to 2 because it's polynomial. And continuous and differentiable everywhere, so don't stress over that part. So now we want to find a C value that matches the mean value theorem. So I will give you the reminder. So I'll say the mean value theorem applies. It means there's a C value in the interval such that this. So I'll give that to you. Okay. And then it'll say find the C value. So we need to really just remember what A and B are, right? There are endpoints. So the left-hand endpoint's A, right-hand endpoint's B. So to fill in this thing, we need to figure out f of b minus f of a over b minus a. So we want f of 2 minus f of 0 over 2 minus 0. Okay. So if we plug in 2, let's see what we get there. I'll make our little notes over here. We plug in 2, let's see this. 3 times 9 minus 4 times 2 plus 1. F2, I get 20. F of 0 is a little easier. We'll just get 1. So plugging in down here, we get 20 minus 1 over 2. Oh, this one's ugly. Did I do that right? Anybody check my math on? Okay, I hope it's not. Let's see. So, yeah. 12 minus 8. Yeah, that's right. Yeah. I think I hit the wrong key for something. Yeah, 5 there. That's better. Sorry about that. We were going to get fractions when I was. We could do it, it's just uglier. So there, that's 4 over 2, so that's 2. Okay. So this part's 2. Okay. Now we need to figure out what f of c would be. I'd just like an expression for f of c. So again, we're just finding the derivative. F prime of c, sorry. So that's 6x minus 4. Okay. So this thing's telling us that 6x minus 4, F prime of c, has to equal 2. Okay. And then we can solve for c. Okay. So 6x minus 4 equals 2. 6x will be 6, x's 1. Just so happened we got 1 again, not always 1. And I said x, that's c, sorry. I'll give you this part. You just need to be able to find the derivative and then just change it to c instead of x. And then just be able to plug in to figure out this side and solve. Questions on that one? Kind of had a lot going on that one. You know, it's not. If you're given the theorem, it's not too bad. Okay. Number 5. Okay. These are good problems. Okay. It says if f of 1 equals 5, and f prime is greater than or equal to 3 for all x's in between 1 and 5, how small can f of 5 possibly be? Okay. So we are using the mean value theorem here. Okay. So we're saying some value in here such that this our endpoints this time it's written, well, I'll get my pen to work. It's written in different notation, but it's just like this. So we're saying f prime of c equals f of 5 minus f of 1, f of 5 minus 1. F of 5 we don't know. That's the one we're trying to figure out something about. F of 1 we do know. What's f of 1? 5. No, we just, yeah, so I see what you're thinking on that. No, because we don't know what f of c equals, but we know f of c has got to be greater than or equal to 3. Okay. So here's what we want to do. We can solve this thing for f of 5. Okay. So if we multiply both sides by 4, and then add 5, I get this. Okay. And since we know this, that means that that expression has got to be greater than or equal to 4 times 1 plus 5. And that is 9. So f of 5 got to be greater than or equal to. So what's the smallest f of 5 can possibly be? That one confusing. We need to go back. It is. It's confusing. Okay, so let's back up. There's another way you can write this down. All right, so maybe it'd be better if that's more confusing. Maybe it'd be better to give it to you on this problem as this. I don't. It doesn't matter to me. So it says this. Hang on, let me make sure I get it right. Yeah. That's like the point slope form. That's like y2 minus y1 equals m times x2 minus x1. So maybe it's easier to start there. Then we can plug in. We would have f of 5 minus f of 1 equals f of 5 we don't know. F of 1 is 5. And then this thing over here just turns into 4 times f prime of c. Because 5 minus 1 is 4. And we can add 5 to both sides. We're just doing the same thing. It's just starting off at a different place. We get there. Oh, so what are I getting? What tells us what? Sorry. F prime of c is greater than or equal to 1. That is. Now it's greater than or equal to 3. I'm sorry. No wonder that was confusing. There should be 3 there. This should be 17. If you do, you have to use inequality because we don't. Yeah. So here, sorry, I guess I saw the 1 over there on the interval, but if we're here, either way you start. If we're here, f prime of c is greater than or equal to 3. Okay. So that means this expression. Okay. Let me just rewrite where we got some more room here. This expression's got to be greater than or equal to 4 times 3 plus 5, which is 17. So that tells us f of 5 is greater than or equal to 17. Yeah. So this one's not in how small can it be? You just do the same. If it's how large can it be, the information they give you will be different. It would say less than or equal to here. If it's at how small can it? I mean, how large can it be? Yeah. And then what happens is everything's exactly the same except this is just flipped. Yeah. We got parts of that we still need to talk about. But let me ask you, let's take a poll. Is it, I mean, I don't care. I guess I could give it to you in both forms. But is it better starting there or starting here? So they're the same thing. But would you rather me give it to you like this? Like that? It's okay. So I might put both on there. You can use either one. It's the same thing. It's just okay. Since you're not having to remember it, since I'm giving it to you, it doesn't matter. Right? Yeah. 6. First, we want to know intervals where this thing is increasing. Looking on the graph. So increasing means we're going up from left to right. So it looks like we're increasing from 1 to 3. And where else? Yeah, it looks like 4 to 6. So between here, here, and then from here to here, we're increasing over these intervals. Okay. And then, oh, left the parenthesis off. -1. Okay. And then where are we decreasing? Yeah, 0 to 1 and 3 to 4. 3 to 4. Okay. C part, I'll leave the graph here where we can answer the questions. C part says where are we concave upward? Yeah, so it looks like 0 to 2. It can be kind of hard to tell exactly where it changes, but on the homework problems, I always put it right on a grid mark, so it's not too bad. So yeah, so we're concave up, 0 to 2, and looks like that's it. We'll concave up. Concave up on 0 to 2. Like down here. That just that point. Yeah, so that point's nothing. That's right. Because on the left side it's concave down. On the right side it's concave down. So nothing special about that. Part D is where we concave down. So we're concave down from 3 to 6. Okay, the rest of it. Even though we got this place right here, it's concave down on this side, concave down on this side, so nothing changes there. We're concave down all the way from 3 to the rest of the graph, so from 3 to 6. And then this one helps you. It says the coordinates of the point of inflection. It doesn't give you the option to have more than one. But our point of inflection would be right there. That's where we change from concave up to concave down. The little sharp corner is not a point of inflection because it's concave down on both sides. So our point of inflection is 2, 2. Yeah, 2, 2. 2, 3 thing, yeah. Yeah, because yeah. A question on that one? Yeah. Concave up, concave. I won't give you any like I won't put a point of inflection at any weird point. Okay. So because we don't have an equation on this one, so we can't figure out exact values unless they're just like right on a grid intersection. I'll make sure we don't have a point of inflection at like 3√3 or anything. Let's see. 7 gives us a graph of the derivative. So that's important. Make sure you realize that the graph we're given is of the derivative of f. And then it asks us what interval is our function increasing. So it's not asking where the derivative is increasing, it's asking where the original function. Yeah, so what that means, okay, if you break it down, right, we said our function is increasing where our derivative is positive and it's decreasing where our derivative is negative. So from looking at the graph, our function is going to be increasing wherever the graph of the derivative is above the x-axis. So that's from 3 to 7. And then what intervals would f be decreasing? That's where the graph of our derivative is negative or below the x-axis. So that's from 0 to 3 and 7 to 10. So if our derivative is down below the x-axis, that means it's decreasing in those places. And then if our graph's above the x-axis, that means it's increasing in those places. And then B part on this asks us at what values of x does f have a local minimum or maximum? Again, this is just a different way of doing like a sign chart. It's more detail. That's right, yeah. So if we were doing it just with our regular sign chart, we would say it's negative over here, positive between 3 and 7, and then negative there. So we've got one of each. We'll go from negative to positive at 3. Okay. So that would be a local, which one? Minimum. Yeah. And so local minimum at 3. And then we go from positive to negative at 7, so that's a local max. Local max. Oh, it doesn't even ask us to specify on this one, but that's good to go ahead and specify. Questions on that one? Hanging in there so far? Hang. One more out of 4-3 here. Ask us for the whole process. This one gives us our function. First thing it asks is where is our function increasing, where is it decreasing? So we need to find the derivative. Okay, so here it's 3x squared minus 12x minus 15. We need to find our critical numbers. Know where this thing won't exist because it's a polynomial, so our critical numbers, we're just focusing on where it equals 0. But we do have a common factor of 3 we can factor from. So it's equal to 0. Divide both sides by 3, makes 3 go away, and then we need factors of negative 5. That will add together and give us negative 4. So negative 5 plus 1. So our critical numbers we're concerned about are x equals 5, x equals negative 1. we can make our little sign chart on the number line. So we need something smaller than 1 as a test value. Oh yeah, -1. Something smaller than -1. Not on top of my game today. -2 would be a good choice. Oh. If we plug in -2, you can plug it into the original. I'm going to plug it in over here to the factor form. Okay, so again, -2, the +3 is not going to change anything because it's positive. Plug in -2, so we'll have -7 times -1, so that'll be positive. So that would give us a positive sign in that region. We need something between -1 and 5. 0 is a nice easy one. So maybe on that one it's even easier to look back at the original. If we plug in 0, we get -15. F prime of 0 will be negative. Then we need something bigger than 5, so like 6. And so if we plug in 6, 6 minus 5 is 1. 6 plus 1 is 7. 1 times 7 will be positive. So in this last region, we're positive. So where are we increasing? We're increasing from -infinity to -1. And 5 to infinity. And we're decreasing between -1 and 5. Any questions on that part before we go to the next? All right. B says find local minimum and maximum values. So if we have any, okay, do we have a local minimum anywhere? So a local minimum would be going from negative slope to positive slope. So yeah, we got one at 5. So the way this one's worded, we want to find f of 5. Because it doesn't ask us where the local minimum happens, it asks us what the local minimum is. So we got to plug 5 in. So let's see, 5 cubed is 125, minus 6 times 25, minus 15 times 5, plus 7. So I got -93. And do we have anywhere where our maximum occurs? At -1. So we'll want to find f of -1. Okay, so let's see, that's -1 minus 6 plus 15 plus 7. So I got 15 on that one. I don't like that they ask C part in the order they ask it in, but they do. So it says find the inflection point, and then it says find the intervals where we're concave up, concave down. We really do all that at one time. So what we need to answer are all those 3 parts, the inflection points, concave up, concave down. We need the second derivative. So we take the derivative of the derivative. There we'll get 6x minus 12. If we set that equal to 0, you can probably handle that one. X equals 2. So when we make our number line, we've got critical number of 2 on there. We just need to test point on each side, so maybe 0 over here. So give us a negative. And then maybe 3 over here, so 6 times 3 is 18 minus 12, so positive over here. So let's do the concave up, concave down first. So we're concave down from negative infinity to 2, where we have a negative second derivative. We're concave up from 2 to infinity, where we have a positive second derivative. The x-coordinate of the inflection point is 2. And then we need to find our y-coordinate. So we've got to find f of 2. So let's see, that'll be 8 minus 24 minus 30 plus 7. So negative 30 down there. Yeah, so, yep. Yeah, you could have more than one inflection point, or you could have no inflection point. So yeah, so when we do the first derivative test, okay, where our sign changes are relative minima or relative maxima, and then when we do the second derivative, where our sign changes are inflection points. Yeah, so with the first derivative, negative and positive are increasing, decreasing, and then with the second derivative, negative and positive are concave up, concave down. The same, we do the same type of stuff, it's just ones we do it with the first derivative and then others we do it with the second derivative. Any questions on that one? Hey. Last few are a little bit shorter, maybe. We're just finding limits. At least not as much writing, probably. So 9 says use L'Hopital's rule if appropriate to find the limit. In order for us to use L'Hopital's rule, we need to be in either 0 over 0 or infinity over infinity indeterminate form. So if we plug 0 in here, in the top we'll get e to the 0th, which is 1, minus 1, so that's 0, minus 5 times 0, so that's 0, so we'll get 0 on the top. The bottom, if we plug 0 in, we get 0. So we are in 0 over 0 indeterminate form. Okay. So we do L'Hopital's rule. L'Hopital's rule says we can take the derivative of the top and the derivative of the bottom, and that'll preserve the limit. Okay. So just do it term by term in the top. So if we want the limit of e to the 5x, we'll get e to the 5x. That one unfortunately is chain rule, so that's times 5. The derivative of negative 1 is 0. The derivative of negative 5x. What's that going? -5. And then if we take the derivative of the bottom, we get 2x. So if we clean this up, so here's the Hospital's rule, and then this is just simplification on this step. So that's 5e to the 5x minus 5 over 2x. Okay. Now if we try to plug in 0, we'll get e to the 0th, which is 1. 5 times 1 is 5, minus 5. Hit 0. Plug in 0 on the bottom. 2 times 0 is 0. So sadly, that's still indeterminate. So what do we do? Remember? Do it again. No limit on how many times we can do the Hospital's rule. It's not always helpful to keep going, but sometimes it is. Okay. So the Hospital's rule says, using the Hospitals here, we can take the derivative of the top and the bottom. So the derivative of 5e to the 5x is 5e to the 5x times 5. That's a chain rule. Derivative of -5 is 0, so that goes away. The derivative of 2x, but 2. That's just 2. You can simplify if you want to, but we're out of indeterminate form now because we clearly do not have 0 in the bottom. So if we substitute in, we'll get e to the 0th, which is 1. So 5 times 1 times 5, 25 over 2. Yeah, no, that's fine. If you wanted to, you could write it 25e to the 5x, doesn't matter. Questions on that one? That one's a little, just not quite basic because it's got the chain rule with the e to the eggs. Not horrible either. 10 just says evaluate the limit. So our starting strategy should always be to try direct substitution. If we try direct substitution, we'll get 1 to the 5th, which is just 1, minus 1, so 0 on the top. 1 to the 3rd, which is 1, minus 1, so 0 on the bottom. So we're in 0 over 0 indeterminate form. So we can use L'Hopital's rule. Derivative is a little easier on this one, so the derivative of x to the 5th, 5x to the 4th, and then derivative of minus 1, 0. On the bottom, the derivative of x to the 3rd is 3x squared. Derivative of minus 1 is 0. We try to do direct substitution now. It works. 5/3. That's 5 times 1 over 3 times 1. Questions on that one? One more L'Hopital. Evaluate the limit. If we try to plug in, we'll get e to the 0th, which is 1, minus 1, so that's 0. 0 to the 5th, 0. So again, we're in 0 over 0 form. So we can use L'Hopital's rule. What do we get if we take the derivative of the top? e to the t. It wouldn't be times t, it'd be times the derivative of t, so times 1. So on this one, that's just e to the t. Yeah. It's easier. All right, we don't have chain rule. And then on the bottom, what's our derivative? Derivative of t to the 5th. 5t to the 4th. If we check when we plug in again, on the top we get e to the 0th, which is 1. On the bottom, we get 5 times 0, which is 0. So what's going on? Can't do the Hospital's rule again because on the top we've got 1. So we're in a 1 over 0 situation. Okay. So remember, the graph here. I think unless I'm missing something on this one, I think it should be I think we should have a from the right on this. Because the graph of 1 over x, what's it look like? It looks like this. So if we did not have the from the right, we got 1 over 0. Now we're approaching 0. So unless I'm missing something, I think it would be D and E if we did not have from the right. If we have from the right, what should it be? We're approaching from the right. This one? Yeah. So got the answer without the plus is infinity, but I don't think that. I'd have to check that. I may be missing something there. But the main takeaway on that one, okay, is not this particular problem, just that once you get into a situation where you're not in 0 over 0 or infinity over infinity form, you can't do L'Hopital's rule anymore. Okay. So like if we'd had, this one would be easier if we'd had 0 on the top, 1 on the bottom, then what would the limit be? 0. Yeah. So I like that problem better upside down. We get 0 on top. Okay. Questions? Well, the web sign showing me infinity, but I'm not convinced on that with unless we're approaching from the right. It may be infinity and I'm missing something, but for sure if we approach from the right, it's infinity. It might just be it's Friday and I'm missing some reason why it would. Oh no, I say, okay, hang on. I do see why it's infinity from both sides. Oh man. Hang on. Nope. So we're thinking about the wrong graph on that. Because here's why it's infinity. It dawned on me now. For sure we get 1 on the top. For sure we're getting 0 on the bottom. Okay. But what happens is we come in from, so if we come in from the right, okay, these are getting bigger and bigger and bigger. So we're dividing 1 by a bigger and bigger and bigger. No, if we're coming from 0 from the right, these are getting smaller and smaller and smaller. So 1 divided by a smaller and smaller number is going toward infinity. That one's okay. The left side, if we're approaching 0, normally if this was just a t, we would have to be thinking about going down toward negative infinity on that side, but it's not just a t. What is it? T to the even power, that's right. So it's going to make it positive. So these numbers are still getting closer to 0, okay, but they're all positive because it's to an even power. So really the graph we should be thinking about is not 1 over x. We should be thinking about the graph of 1 over x squared, and the difference there is this. It goes up on both sides, so it is infinity. Yeah. Okay. All right. Other questions? Okay, yep.
So could I just start plugging in?
You could, yeah, you could always plug in some test values to give you an idea. Yeah, no problem. Yep. Yeah, that's always a valuable tool, so if you're stuck. Alrighty.